Welcome to today's seminar talk, which is being organized by Transport Educators. And University of Ghana, welcome to the seminar talk also. And to Dr. Tomar, welcome and thank you for agreeing to give this talk. Dr. Tomar is a senior research scientist at RICAM, or the Austrian Academy of Sciences. His research interests is in the area of applied and computational mathematics. After finishing his PhD in 2001 from the Indian Institute of Technology, Kanpur, he worked as a postdoctoral fellow at University of Twente, Netherlands, till 2004. Since 2005, he has been working in RICAM. Currently, he's leading a research project with 2 PhD students and is a co-investigator of National Research Network project, both funded by the Austrian Science Fund. In 2002, he was awarded Dr. Shankar Dayal Dharma, Honorable Ex-President of the India Medal for outstanding all-round contribution in the graduating class of the postgraduate programs of study. And in 2009, he was awarded J.T. Oden Faculty Research Fellowship to collaborate on research with Professor T.J.R. Hughes, ICES, of the University of Texas in the United States. So having introduced the speaker, we can start now.
Thank you, John. Thank you for introducing. I hope everybody is able to hear me clearly.
It seems that they went out of the listeners window, so let's give them a couple of seconds for them to get back into the listeners window then. Yeah.
Okay, so could you please change the slides?
Yeah, just I'll change the slides and then I will hand over control back to you.
Sure.
Okay.
Yeah, start now, John?
Yes, you can start now.
So good afternoon, everybody, and thank you, John, for introducing me.
You are now muted. You are now unmuted.
Okay, I presume that there is no problem. So feel free to stop me anywhere if you have any questions. This is the whole purpose of this webinar, so that this is interactive. If you have any questions or if you have any doubts of any things which is being presented in the slides or what I'm saying, just feel free to stop it and ask me. Okay, so the first thing I'm assuming here today that all the audiences, they have not been exposed or they have not worked in finite element method. So this is the fundamental assumption. If any one of you have anything done in past on finite element methods, then you may find all this matter very, very introductory, and you may find it's a waste of your time. So feel free to leave if you know any of the things here. This is specifically tailored to the audiences which have not been exposed to finite element method. So before I begin with my scientific method, these are few words I would like to start with. In a completely rational society, the best of us would be teachers and the rest of us would have to settle for something less, because passing civilization along from one generation to the next ought to be the highest honor and the highest responsibility anyone could have, by famous industrialist Lee Iacocca. Okay, so here's the outline of my presentation or a lecture, whatever you feel like. First, give you the motivation why there is a need for finite element method. So I'm presuming that at least you have been working in finite difference methods and whatever problems you have solved with that. So after this motivation, I will take you to the weak formulation. What is the weak formulation? What is the need for that? Then we will talk about the Galerkin finite element method, the most prevailing approach in finite element method. There are different variants, different possibilities. The finite element method, if you search in Google, you will find millions of articles or books basically. So we will be focusing on Galerkin approach today. And then we will be talking about some particular example which I will be taking you through. So it's like a hands-on experience. So I will drive all the things, all the equations, all the matrix terms, the right hand side vectors, so that you can see yourself how it is working. And then finally, I will be presenting some numerical results. I will be showing you from my desktop here, from my laptop, some MATLAB functions basically, and I will be showing you some solutions. Watch it. Basically, the graphs being plotted, errors being computed. And finally, some concluding remarks. So it is going a little. That's fine. Okay, so here are some references. I think I need to take it this. That's better. Some of the references on finite element methods. There are numerous excellent books, not just one or two. So I have just listed here few of them, very few of them, which I have gone through myself or which I find really very easy or best suitable for this kind of audiences. And they are in alphabetical order, not in the order of they appeared. Okay, there is one typo here. So the first book is by Professor Dietrich Breiss from Germany. So Finite Elements Theory, Fast Solvers, Applications in Elasticity Theory. Cambridge 2007. Susanne Brenner and L.R. Ludwig Scott, The Mathematical Theory of Finite Element Methods. They both are very good books on theory and with a gentle introduction to these finite elements. P.G. Charlotte's book, this is SAM 2009. It's not 2009, I'm sorry, it is 2002, and the first version was published in 78. This is considered by most experts as the classical book on the finite element method for elliptic problems. Then those who are interested in implementing the FEM, and implementing the FEM book, the finite element method by Gockenbach, published from SIAM in 2006. Then from one of the really the fatherly figures of finite element method, Barna Sabo and Ivo Babushka. So Professor Babushka was among the pioneers who started working on very early on this finite element theory. Early 70s, they have published their papers. This book is also, I think, some mistake here. I mean, maybe when I was compiling, I made a mistake. It is 91. The book is from 91. And this Zinkwick, Taylor and Zhu book, The Finite Element Method, Its Basis and Fundamentals, published by Elsevier in 2005. So my apologies for these two mistakes here. Typos. The Sabo and Babushka book is published from 91 and Charle book is from 2002. So I'll correct this and finally I'll give this to John and Neeraj. Okay, so let's start with our first point. Why finite element method? So consider the Poisson equation in a bounded domain, omega, which is a subset in d-dimensional domain. So dimension could be 1 dimension, 2 dimension, or 3 dimensions. So we start with very simple model problems so that I can present the ideas in a very neat and clear way. Otherwise, you will be lost in a lot of stuff basically. So Poisson equation in omega and boundary conditions. The abbreviation I'm using here is BC. These will be specified later. So I do not want you to be lost at this moment what kind of conditions I'm assuming here. So this is the equation here for an unknown function u, where the right hand side function f is assumed to be square integrable. I presume that you all are aware of L2 space. Lebesgue integrable, square integrable space. So f is assumed to be given here. Okay, so physical examples. I mean, this is very simple problem, as I said, model problem, but this can still represent several phenomena found in the real life. For example, steady state heat conduction, electrostatics, deformation of a thin elastic membrane. May also be required, a solution of this Poisson equation may also be required as part of more complex problems like Navier-Stokes equation or Austrian equation. Okay, so a solution of this problem, a smooth function which is twice continuously differentiable in the whole domain. Yeah, so I will try to basically, yeah, let's see. Just a moment. So, yeah. The function u has to be twice continuously differentiable inside the domain omega, and it has to be continuous up to the boundary. So when I say omega bar, then it means it includes the boundary of this omega also. So this smooth function which satisfies our model problem Poisson equation pointwise, this is important here, that it satisfies pointwise, is called the classic solution or strong solution. Okay. This necessitates the assumption that at least f has to be a continuous function in omega, or stronger even, that it has to be continuous up to the boundary. But this still does not guarantee the existence of classical solution, as I will show you in a moment here. Okay, so when the domain is not smooth, so as I was saying just now, that you still may have sufficient regularity for f, but your solution may still not exist, the classical solution. So when the domain is non-smooth or the function f is discontinuous, the function u may not be smooth, sometimes called regular, smooth enough or regular enough to be regarded as a classical solution. An example here, consider the L-shaped domain where u, so I have to again use the pointer now here. So this is my domain here, this L-shaped here with the boundary here, and at this point the solution is not second order differentiable. So the expression for u, analytical solution here, is r to the power 2 by 3 and sine 2 by 3 theta. You can clearly see that this can be, I mean, more and more you take this angle here. For example, if I take the space like here, I mean the domain like up to here, then the singularity is getting worse and worse here. So despite, for example, even if I choose right hand side to be equals to 0 here, which is perfectly smooth, but still this solution does not exhibit the second order differentiability at the corner here. I may give you some more example just now. As I said, that if I start taking, instead of this line, if my domain is over here and it goes like this, in these situations it is difficult, if not impossible, to come up with some finite difference schemes. Yeah, you can come up with very complicated geometries where finite element method has been used for a long time, but it will be a really very cumbersome task to devise your finite difference. So such problems, okay, there was a good time for finite difference. I mean, till 30s, 40s, 50s, a lot of problems were solved on that. Even there are some specific problems where this is really still the method of choice. But for general geometries, a lot of physical problems being considered by engineers, it has been solved by finite element methods and rather easily. So now, once again, the repetition of all the points here in the slides together. A smooth function u which satisfies one point-wise is called the classical solution or classic solution. And in this example, this L-shaped domain, it fails to have this second differentiability, this C2 omega. So this is one reason or one class of problems why we need to go for finite element method. Okay, so what is the, after the strong form or strong solution, what is the weak solution or weak formulation? For problems with reduced regularity, like just the case I presented here for L-shaped domain, which arise from perfectly reasonable mathematical models, an alternative description of the boundary value problem, abbreviated as BVP, is required. Since the alternate formulation is less restrictive in terms of the admissible data, it is called a weak formulation. To derive a weak formulation of our model problem 1, we require that for an appropriate set of test functions. So in this lecture, I'm not going to provide any theory. So when I'm saying appropriate, then okay, they satisfy certain conditions, which I will introduce eventually, but I will try to avoid giving you really the rigorous theory for all this. So the following relation holds. So integral, I mean, we had this Laplace equation Laplace operator and inside. So now we ask that the weak formulation is such that together with V, these relations hold in integrated sense, provided the integrals are well defined. So note that if U is a classical solution, then it must also satisfy 2.
So one quick question here. Do you mean to say that, in a sense, are you talking about the weak derivative of the test function V or? Okay.
Right. So this I'm coming next basically. So this is the starting point and I'm coming next to that.
Okay.
Yeah. So when I say appropriate set of test functions, so we will be using some property from this V and we will be shifting something from U to V. Okay, so this is again a recall of all this slide, the matter of this slide. Okay, so now if U is sufficiently smooth function, that's what I'm saying, that I was saying that appropriate set of test functions V. So one appropriateness is that they should be sufficiently smooth. Then the smoothness required of U can be reduced by using integration by parts, that is derivatives. So I will use abbreviation I dot E dot, that is used for that is derivatives of a product rule and divergence theorem. So we had this minus Laplace U V. So we integrated that, one derivative is shifted to here V. So now it is Nabla operator. That means grad U, partial U, partial X and partial U, partial Y in 2D, and you include partial Z in 3D also. And remember, this is really a dot product here. Now this is a product between two vectors. It's a vector of nabla U and nabla V. So if V has sufficient regularity, it means it is at least first order differentiable, then we can shift some derivation from U to V here, which was required initially to be in Laplace, second order differentiable. And then, so the remaining terms, the right hand side is as such here, and the remaining terms here, it goes with V and partial U by partial N. This is the normal derivative N dot grad U, I can say. This is on the boundary of the domain here. So far, I'm not talking about anything about boundary conditions. I'm just going through with this Poisson equation. Any questions so far? Anybody? This is just integration by parts here of the Laplace operator.
So I guess, it makes sense here in this case, since we're talking about the normal to the domain, that the domain has to be smooth. So here, this is where the smoothness of the domain comes into play.
That's right.
Okay.
It has to be piecewise analytic.
Yeah, piecewise analytic. Okay.
Smoothness, yeah, I mean, in the sense it can have the corners. It is, we are not excluding the corners here. Yeah? So the problem 3 may have a solution U called a weak solution that is not smooth enough to be a classical solution. If a classical solution exists, then 3 is equivalent to the model problem 1 and the weak solution is classical. So now what we need here, what we are asking now here is the existence of integrals of first order derivatives. Specific forms will be coming now. So we are now in the space of functions. I will try to keep this to bare minimum. Don't get afraid of that. So what we are talking about, we use the space of functions that are square integrable in the sense of Lebesgue. For example, that is this L2 omega space here for our domain omega. Those functions whose square and integrated over omega is finite here. And we use the L2 measure. This is our L2 norm here. So you take integral over omega square of V and then you take its. So the integral, what we had on the left hand side in our previous equation, nabla U, nabla V, a dot product of that. It will be well defined if all the first derivatives of U and V are in L2. If they are not, then we cannot say that this relation, I mean this integral can be computed or this exists. For example, for D equals to 2, two-dimensional problem, two-dimensional domain, we require that Ux, Vx, Uy, Vi, they are all in L2. If we are in 3 dimension, then you can include here Uz, Vz also. And this is precisely the Sobolev space and is defined by, we use the notation here H1 omega. So a function v which takes all the points which maps to r from omega, so that all the functions v, vx and vi, these partial derivatives, they are all in L2. I'm not talking about any boundary conditions so far. Bear in mind, please. Okay, so similarly for the right hand side, the integrals fv, the product of f and v, it is not an inner product, they both are scalar functions, and this v, the normal derivative of u, it demands that f to be in L2, and similarly this function, the normal derivative of u, to be in L2. Actually, to be very precise, this normal derivative of u could be in h minus half. But I'm not sure if the audiences are well versed with Sobolev spaces theory, so I'm rather keeping it simple just to be in L2. That is, h minus 1/2 is also a subset of this L2 here. No, that's a bigger space, but anyway, this is sufficient for our purpose right now. Okay, so recall of all these spaces here, spaces of functions here. Now I'm coming to the boundary conditions and what respective Sobolev spaces we need. The space H1 omega is the space where a weak solution of 3 naturally exists. As I just explained that all the partial derivatives, they are in L2, so all the integrals are well defined. Note that this one can derive and one can found in some books also that if a function v is in H1 omega, it means it is if and only if, or it gives and it comes from the condition that v is continuous function on omega bar. It means up to the boundary. So if a function is continuous up to the boundary, then this function is in H1. This suffices for our purpose of this lecture. Or the problem the model problem we are considering. So now assume that our boundary is decomposed into two parts, gamma d and gamma n. Gamma d will reflect the Dirichlet boundary data or Dirichlet boundary condition is specified, and gamma n the Neumann boundary condition. And they have an empty intersection here. This is an empty set, and we also assume that gamma d is non-empty. That means at least one point should be basically on Dirichlet boundary. And the boundary conditions are given by that u equals to gd on gamma d and the normal derivative of u equals to gn on gamma n. So with this, now we have this space of h1 omega. Now we introduce the non-homogeneous Dirichlet data in our space. So vd, we denote this by vd, which is h1 sub d and omega. So v is in h1, so all the functions we introduced before this h1 space. Additionally, we assume here that, or restrict here that v to be equals to gd on the gamma d on the boundary, Dirichlet boundary. And the space with homogeneous data. Yeah, so this was with non-homogeneous, we used here d. Now we use here 0, so that this function here is equal to 0 on the Dirichlet boundary. A recall of all the points here on the slides, if anyone has missed something. So the final weak formulation, we had the solution of this equation which we obtained after integrating by part Laplace operator together with the boundary conditions is the solution of the following weak formulation. Read this. Find u in the space h1d omega such that the left hand side is integral over omega nabla u the dot product nabla v. Right hand side the integral is still on omega with f with v, and on gamma n we have this g and v. So the gn was our normal derivative of u prescribed on the gamma n. For all v on h1 0. Is this point clear to how we could come up to this equation here? Okay, I assume. The point here is that the whole boundary of omega, as I mentioned earlier, this is the union of gamma d and gamma n. So on gamma n we have this condition, but on gamma d this del u by del n, partial u by partial n is not defined. So in order to this integral to be well defined, we need to make this v to be 0, so that it is 0 then. So then all the terms in this equation are well defined. And this is why we need this space H10. And for U, of course, we have some Dirichlet data, so it must satisfy those Dirichlet boundary conditions here. So this is the difference we seek. We find U in H1D, whereas V is from H10. I hope I'm able to clear this point here. Okay, now recall that classical solution required twice differentiability, whereas weak solution requires only square integrability of first derivatives. This has been the major driving force for the development of finite elements. So now we come to the Galerkin finite element method. So far we were at the continuous space, now which is infinite dimensional. Now we are coming to the finite dimensions. So assume finite dimensional subspaces of these three spaces V, Vd, and V0. Recall that V was our Sobolev space H1, Vd was our Sobolev space H1 together with the non-homogeneous Dirichlet data, and V0 was our H10, that means Sobolev space with zero homogeneous Dirichlet data. So now we assume this VH to be a finite dimensional subspace of V, VHD finite dimensional subspace of Vd, and VH0 as a finite dimensional subspace of V0. So the statement of Galerkin finite element method. So find UH in VHD such that, so basically I am replacing all the continuous functions by their finite dimensional counterpart here. So nabla UH, nabla VH. So this sub H, subscript H, this signifies the finite dimensional situation here. So everything else is just same here. So functions F and Gn, they are still to be exactly integrated and evaluated. Naming. So basically, there is one professor in Switzerland. He has been doing quite a bit of research on who invented this Galerkin method or finite element method and where are the roots or where the roots can be traced back. It was Swiss mathematician Ritz which came up with this kind of ideas in the beginning, and then Galerkin started using that, and then he basically made it popular and he derived all these theories afterwards. And of course, Sobolev made fundamental contributions to the theory of partial differential equations. So when we use the same trial and test functions, so now I have not said anything about trial and test function. So the functions for UH which are used to approximate UH, these are called trial functions. The functions which are used to approximate VH, they are called test functions. So when we take the same choice for both of them, then the method is called Bubnov-Galerkin method or Galerkin method. And if we choose different trial and test functions, then it is called Petrov-Galerkin method. Okay, so now we are in finite dimensions. So let phi 1, phi 2 and all up to phi n. So there are n. This be a basis for VH0 with homogeneous Dirichlet data, Dirichlet boundary condition. And apart from up to phi n, the remaining 1 to capital D, which signifies the Dirichlet data, be a basis for VHD. So this is a basis here. Now when we are talking about finite dimensional space, so it has a basis, right? So this whole space can be spanned by these basis functions. And so we approximate our, so in last slide we had the integrals, but this is still in a polynomial form. How do we represent that? What kind of basis we use? So we are coming to that point now. So UH is in VHD and VH is in VH0 as follows. So VH is approximated with these basis function with some expansion coefficients of that. Yeah, because these are the basis, these phi j's, they form the basis for VH0. And additionally for VHD, we need phi j not only from 1 to n, but additionally from capital 1, n plus 1 to n plus capital D. So these phi j's are called trial or shape functions sometimes, and uj, they are called expansion coefficients. Now, so far I have not specified which kind of basis functions I'm going to use, which kind of polynomials I'm going to use. If, for example, if you are using the Lagrange basis functions or Lagrange polynomials, then these are the pointwise values. UJs are the pointwise values. It means after you have solved your system of equations, at the end, the values you will be getting, these are the real U values at those points. But for example, if you are using integrated Legendre basis functions or monomials, then this is not necessarily the case unless you are using only the first order polynomials. Okay, so using the approximation we just wrote here, we obtain for all. Yeah, when we say for all test functions, it means in this space you can consider one function with any coefficients here basically, and that's why it is written always in this form of for all I, any course space, any coefficient for that. But for uj, this is the unknown variable we need to find out, we need to compute, we need to solve the equation for. This has to be kept in the equation. So this equation is for a given I, any I you can choose from 1 to n in the basis we have. Then this summation of j equals to 1 to n uj phi j. This was the approximation of u h, and this comes from the approximation of v. Now we are in the finite dimensional spaces here, and we are approximating it using the polynomials. And then everything else I have just substituted UH and VH by their approximations. Okay, so this is a recall of all the points in this slide here. So finally, with all these things, so the system 8 can be written in the matrix form as capital A, capital U equals to F. This is the matrix equation we will solve on a computer. So A, the matrix A is found by this Aij for all 1 to n and Fi for all 1 to n, I1 to n. And Aij, these entries of this matrix capital A, they are the integral of nabla phi I with the dot product of nabla phi j. So this will be a square matrix. Ij, they both are varying from 1 to n. And the right hand side vector Fi with the entries Fi is given by this equation here. The linear system of equations, and this is called the Galerkin system, and A is the stiffness matrix called, because these finite element methods of the first fundamental work were presented by engineers, so they were dealing with the problems from elasticity, so this is how the name came up with this stiffness matrix. Note that A is symmetric and positive definite, for which I will use the abbreviation SPD, and thus guarantees a unique solution. For pure Norman problem, A is only SPSD because there is no data basically. I will just show you here which can tackle the semi-definiteness. It will at least make one row to be 0. So, and VH, this is space V because there are no bound additional data there. So we have to talk about only VH. This needs to be constrained with this condition here for uniqueness. Once again, a recall of that. So if we do not have a Dirichlet data, then this problem is not, this term is not there, and then this term AU equals to F is not uniquely solvable. It is a singular matrix. Okay, so now I'm coming to the last part here basically. When I'm talking about working with one-dimensional problems, so hands-on experience in that. So it is easier to write 10 volumes on theoretical principles than to put one into practice. And I always make it a point with my students that they know what are the things going on, at least they have some working experience. I very much like this quote from Leo Tolstoy. So working with one-dimensional example here. So consider now the Laplace Poisson equation in 1D. Minus second derivative of u equals to f in omega, a unit interval 0, 1. So I'm just writing for the sake of simplicity here this 0, 1, but I will show you in my computer program that you can choose any boundary data, homogeneous, non-homogeneous, or including that domain, it is not necessary to be 0, 1. It is very easy to write, make these changes, subtle changes here. The Galerkin finite element method reads here, find UH in VH0. Now because we have the display data with 0, so the space VHD, this coincides with VH0. So now we have the same space exactly for VUH and VH. So now this is the equation we have. There is no nomenclature, there is no additional term here. And the third term on the right hand side, that is 0 also now, because we have the 0 display data. Okay, so on this interval 0, 1, let's assume that we have n nodes, x0, x1, xk minus 1, xk, xk plus 1, and xn. Altogether they are n plus 1 nodes. So this is a sequence of non-decreasing nodes here, strictly increasing, I must add here. And let capital K, small k, sub k. So when I say capital K, this denotes my an element. But small k, it takes the index for a given element. Yeah, so this is an element from xk minus 1 to xk. This is the interval. So there are n elements now. It varies between 1 and n. So let this be a general element. Size, for example, for this one, so this is my capital K sub k element here. So the size of this will be xk minus 1. And let this h be equals to maximum of all these hk's for all the elements. So it is not necessary that you use the equidistant points, not at all. You can devise, depending on your problem and depending on your interest, devise any scheme here. You can have any kind of grid node arrangements. So then if it is non-equidistant, then we must talk about something, this h, and which is called mesh parameter. If it is same everywhere, then it is also just fine. So for approximating u sub h, we choose the space of functions continuous piecewise linear functions. Yes, this is really the example we need to work out. So previously we said they are just finite dimensional spaces. Now we need to specify what are these functions. So VH0 space is now Sobolev space, the functions from the Sobolev space, such that the restriction of VH on a given element k with sub k on a given element k, this is a polynomial, linear polynomial. So for any given element kk, we have a linear polynomial. So this is a space of polynomials of first order. And this is for all the elements. Additionally, at the first node, I mean the 0th node and the last one, the value has to be 0. Remember, we are assuming now homogeneously bounded data. Okay, so this is a recall from the problem setup from this slide. So for the basis functions of the space VH0, we use the hat functions associated with the nodes xk. These are defined for all elements k by, so this you can clearly say this is the Lagrange polynomials, Lagrange interpolating polynomials. So x minus, so if it is, so we are talking about the basis function associated with this node xk. Yeah. So if we are on this side of the element, or rather on this element, then the function has to be x minus xk minus 1 divided by the element size here, hk. And if it is on this side, then this is xk plus 1 minus x divided by the element measure here. And it is 0 elsewhere. So these are the functions which has very local support. Yeah, so they are 0 everywhere else other than 2 elements with which they are sharing. I have used here equality in both the cases. So, but it does not violate any condition. Remember, we are talking about the continuous piecewise linear functions. So they are linear certainly piecewise, but they have to be continuous. So for example, if I take x to be equals to xk here, so at this point, so this function from the left side is 1 here. Yeah, because xk minus 1 is my hk, so hk by hk is 1. Similarly, this value from this right side is also 1 here, because if you take x equals to xk, so then xk plus 1 minus xk is my hk plus 1. So there is no discontinuity here. These are continuous piecewise linear functions. So the derivatives of the basis functions for all k, they are given by, you simply take a differentiation here, 1 over hk and minus 1 over hk plus 1 and 0 elsewhere. So this figure is basically for the next argument here. I could not find other place, so I had to basically arrange here. Okay, so for any element k with subindex k, small k, the basis functions, there are two basis functions, phi k minus 1 and phi k. So this is a mistake here, it should be k here. My apologies here. So this is your element. We are in interval now, xk minus 1 to xk. So this basis function is coming from the element before, if you try to recall from this one. So this is this lag of this basis function associated with this node. And then associated with this node, this is the next basis function here, which is going up to the next element. So this is written here phi k minus 1, this is written here phi k. And this is the element kk with nodes xk minus 1 and xk. Okay, note that these functions are continuous and piecewise linear. I repeat here. So there is no violation of any of the conditions of the function spaces. So the finite element space can be expressed as VH0, which is spanned by all these basis functions phi k for k0 to n. So when I'm talking about the element, then I'm taking the index from 1 to n. But when I'm talking the basis functions associated with the nodes, then I have to take the index from 0 to n. So any function in VH0 can be expressed as a linear combination of the hat functions, because this spans the whole space. So depending on the coefficients you take for the linear combination, you can express any function in this space. And so now using this x approximation for the UH and written like this here, summation from 0 to n, uj phi j. So these are the basis function now, phi j from 0 to n index. And now uj means u evaluated at xj. So this is specifically for these kind of basis function. In fact, for all order of basis functions, whether you talk about hierarchical basis functions or you talk about monomial basis functions, the first set has to be this hat functions, so that stays same. But when you start increasing polynomial order, then the additional difficulties or additional variations starts coming up. So the finite element method can be equivalently written as, I take sum of j 0 to n with uj, integral the whole domain, now 0 to 1, phi I prime, phi j prime. There is no dot here because this is not really a vector now. In 1D they are scalars. Excuse me. And the right hand side is integral of f with phi I from 0 to n. Okay, so this is the recall here for this slide for all the points here. Now, when we are working with complicated geometries, especially in 2D and 3D, it is a tedious and often error-prone task to devise basis functions for global coordinates x and y and z, depending on which dimension you are. So that's why the integral, the previous integral we just showed, this has to be decomposed into integrals over elements and then summed up. This is where the term element is coming from. So for above mentioned reason, again, this complicated geometries in 2D and 3D, the physical elements may not have a simple shape. For example, in 2D, like square or a triangle, basically isosceles or these kind of triangles. So if they are very distorted, so in practice, it would be difficult to work with them for every element to keep a track of that. So therefore, in practice, we work on a reference element which is denoted by k hat. And each element k of omega is a smooth mapping from k hat. And of course, if we do not have the same element sizes, for example, x minus 1 to xk, if they are not equidistant, then these maps will be different. Okay, so now working on a reference element. So k hat I work with personally as -1 to 1, which is also quite often used. I may say this is a majority of the choice, but other people also use 0 to 1. And prominent personality also uses 0 to 1. So there is no issue with that. You have to devise your basis functions, and then you have to basically work with the integrals and the quadrature formula according to that. And then each physical element, now I distinguish between a physical element and a reference element. Physical element is from our domain omega, and the reference element is this k hat. This be a mapping of k hat. So all of them are mapping of k hat with a different mapping. So let fk be a mapping from this standard element, reference element to kk, and this is an affine mapping. If we go for higher order, then we need to go for isoparametric mapping. Right now we are linear polynomials, so affine mapping is good enough. And in fact, if we have a smooth boundary also, if we have a straight-sided boundary, then affine mapping is also sufficient, even for higher order polynomials. So this is the mapping. If we go from xi, so now my coordinates in the reference elements are xi, -1 to 1, and in the physical element they are x. So this is the mapping, xk minus 1, x equals to xk minus 1 plus hk by 2, element size divided by 2, and 1 plus xi. And if I write an inverse mapping of this is a smooth mapping, perfectly differentiable. So xi equals to -1 plus 2 by hk x minus xk minus 1 for all the points from this. So you can map from both sides, xi to x and x to xi. You can work out the details yourself. These are very elementary algebraic derivations. So then xi, when I write, this is the derivation, so this is partial x by partial xi, or in fact in 1D this is the full differentiation. So dx by dxi is my hk by 2, and dxi by dx is my 2 by hk. This will be needed in our evaluating the integrals. Okay, so on k hat we have the basis functions and derivatives as 1 minus xi by 2 and 1 plus xi by 2. You can see that clearly at the endpoints, -1 and 1. Only one of them will be 1, the other one will be 0. They form the delta, Kronecker delta. So if I take xi equals to -1 here, then it is the value of this basis function is 1, and the value of this basis function at xi equals to -1 is 0. On the other hand, for xi equals to 1, this basis function is 0 and this basis function is 1. And their derivatives are -half and half. So again, a recall of all these points here on the reference element. Now to compute elemental stiffness matrix, we map to k hat and we obtain. So this was our excuse me, elemental stiffness matrix A sub k, with this interval xk minus 1 to xk, phi I prime with x, phi j prime with x, and in this measure here, infinitely small measure dx. This is the first slide I'm seeing, and I think this is the only slide, because I need to distinguish between two coordinates. So this is for ij 1 to 2. So if you work with the global basis function, you can write it like this. But if you come to this reference element here, so you map -1 to 1. Now d phi I by dx will be d phi I by dxi and dxi by dx. Similarly, d phi by dx, excuse me, d phi j by, excuse me, d phi j prime by dx. My apologies again. D phi j by dx will be d phi j by dxi and dxi by dx. And now when we are mapping the from this element measure also, so from dx we will get dx by dxi and dxi. So this term gets cancelled out. What is remaining is xix here. So xix we just saw in the previous one. It was 2 by hk. So we will get here 2 by hk, and all these terms are, the derivatives are -half and half. So if you take a product of that, it is 1/4, and 1/4 when you evaluate the integrals basically from -1 to 1, you get those factors cancelled out. So this is what you get. You can check this with the global basis also. Okay, so similarly, the elemental right hand side is obtained as, so f sub k, this is the element, this is what we need to evaluate. And here, so we need to write now this x in terms of xi. Here it was just, you had the basis functions, but here you really need to write down this x in the form of xi. And this is the basis function, this is fine here, but this xi comes from the map here. Okay. So we have done, now so far we have evaluated the elemental integrals. How do we go from here to the global? Of course, the problem we are given is a global problem. We do not have a local problem. So every element had two basis functions and two nodes, one here, one here. Similar, this one here, one here. This one here, one here. So this with cyan color, these are denoted as the elemental degree of freedom and the basis functions. When you go to the global problem, so you start putting these entries in the matrix at the same position from both sides. So the second contribution from this element and the first contribution from this element, this will be added, and this will give us the contribution, one single entry here in the global matrix. So this is done for all the internal nodes. And in our problem, we have Dirichlet data at the endpoint. So that's why I'm keeping here with this different color, magenta. So after we have assembled the system will be still, for example, this is an 8 element decomposition of our domain. So we will have a 9 by 9 system, 1, 2, 3, 4, 5, 6, 7, 8, 9. And out of that, these two values will be the Dirichlet data that will be eliminated from the system before it is solved. Okay, so finally, this is we assemble the element matrices into the global system by using local to global node mapping. I have not provided an algorithm for that. I mean, this can be found basically in many books. So I have not, because of the restriction of time, I have tried to keep it bare minimum here. So this is the matrix you will be getting. So where you see this entry of 2, this you can associate this with the squares, that where the contribution is from the neighboring elements. The RHS vector, the right hand side vector, is also similarly assembled. Okay, so now comes the final part of this, incorporation of the Dirichlet boundary conditions. So assume that the node xm lies on Dirichlet boundary with the data value given gm. So I'm using just for this node number. In our case, I know this is 0 and n, but it could be applied to any problem. So I'm just keeping it general here. So then to enforce um equals to gm, what we said is that we set the entry of the matrix to be 1, the diagonal entry, I'm saying amm, and all other elements in that row of x we make it 0, except this m. That's why I'm saying here this is only the diagonal entry, and for all other i's this is made 0 here. And the right hand side value is taken equals to fm equals to gm. So if you recall, our linear system is au equals to f. Yeah. So if the value is g and the coefficient of the matrix is 1, we clearly get um equals to gm without any problem here. However, there is some issue with this. This will destroy the symmetry of the system. Recall, our original system was symmetric and positive definite. So if we make some changes only in the row, then our symmetry is destroyed. So what we need to do, and this is important for fast iterative solvers, for example, conjugate gradient methods, where we need the symmetry. So what we do is that to restore the symmetry, we modify the mth column also of the matrix A and the vector F, such that from the matrix, if you recall this column, so if we take the entries of those things on the right hand side, so my fi equals to fi minus, so this is the column entries for this nth column multiplied with the value of the what is the Dirichlet data at that point. So this we subtract on the right side, and then we make this aim to be 0 for all those Dirichlet data points. So this way we have restored the symmetry. So now the mth row and column will be all zeros except the diagonal entry to be 1. And that can also be basically excluded. I mean, you can still reduce the matrix size by 1, just eliminate that. Only after doing this, basically, when you make this perfectly symmetric here. Another approach which is commonly used in practice is to set this diagonal entry to be a very large number. This is epsilon to be to the power -2, and epsilon is a very small number, yeah. And then the right hand side, the true value, the true Dirichlet value at that node, multiply that number with the same amount here. So what you will get, all other numbers will be very small in that matrix row and column. So effectively, what you will get is this simply UM equals to GM without changing anything in the global system. So when people work with very large problems, then this is the often preferred choice. You do not have to eliminate any basically contribution from anywhere. Okay, so you need to repeat these points either 1 and 2 or 3, whatever approach you are using, for all nodes lying on the Dirichlet boundary, and solve the reduced system. The reduced means then I'm taking this mth nodes out from the system. You can leave it if you are following this third approach here. So finally, you have got some AU equals to F. If you solve that, then you will get U values at the node points. Okay, so this is the recall of all these points here. So I'm coming to my concluding remarks. Of course, as I have promised before closing, I will show some numerical results also. So John, I'm going to share my desktop now.
Yeah. Okay. So hold on a second and let me set it up. Hold on 1 second.
Please.
Mm-hmm.
Can I start the program now?
Yeah.
Okay. So if the audience are able to see, this is my program here. I call it solve func. This is the main function to solve this problem. The argument of here are P, the polynomial degree, N, the number of elements, and L is the refinement level. I have not introduced in my lecture the refinement level. You do not need to worry about that. This only shows that starting from any given level, how many refinements I can get and what is the order of error and what is the order of accuracy I'm able to achieve. It is perfectly fine because I'm running here. This is from 1 to L plus 1, so I can take L equals to 0 also without any refinement. Okay, so some other values here. I'm going to approximate a trigonometric function, a sine 4 pi x on an interval 0 to 1. So these are my basically the domain. This is my domain 0. This is the beginning point. This is the end point. This is the length here, h here. So I will be changing it afterwards. I will show you that it is. I take any domain coordinates here. And this is the sine 4 pi x. I can choose it to be a constant function, a polynomial x, or a polynomial, say like of higher order, or a trigonometric function. I can define whatever functions I want. What I need this function is for the right hand side. Remember, we need this f data available and the Dirichlet data. But we want to test this program, so we just want to see what our function analytical solution and its derivatives are. So these I pass in as an argument u, and this is the right hand side function, and this is the derivative to compute my error. How to compute an error, how to judge the quality of our approximation, these points I have not talked. Of course, in 1 hour lecture I cannot include all the things here. And these are the possible choices. So I can choose my analytical solution to be 1. As you can see here, 1, so its first derivative and the right hand side will be 0. If I choose a function to be of type x, then its first derivative is 1 and right hand side is to be 0. If I choose to be x squared, then it will be 2x and minus 2. Remember, in this case, both the cases x and poly, our right hand side Dirichlet data will not be 0. It is 0, and in fact, even in this case, yeah. With C, X, and poly, in all of these cases, our right-hand side Dirichlet data is not 0. We are using non-homogeneous Dirichlet boundary condition here. Or in the trigonometric case, the trigonometric function, this is sine 4 pi x. There it is 0. So I will start with this sine function. Did you see the plot, John?
Yeah, 1 second, let me just, yeah.
Do you see it?
Yeah.
Okay. So this has the scale of 10 to the power minus 15. It means it is effectively 0. It does not make any sense. Why? We are using only 4 elements to approximate a function sine 4 pi x, which has already basically 2 full waves, right? So this is not enough here. Okay. What I do then is I increase this number to, for example, 16. This is the wave, the shape of the wave we start reflecting now. Okay. So what we can do now, I will show you here, and this is the program which is computing here my error also. What is the order of error here? And this is an H1 error computed in this Sobolev H1 norm, and this is the L2 norm. These both errors are computed here. So what I will do here is now I will run a loop of how many refinements I want, for example. So this is my polynomial degree, first degree. I start with my 8 elements and I will refine it starting from the first level, then I will refine it 10 times. And then you will see how the shape of the approximating function is changing. The first level, this is what we have, a sawtooth wave. This is the bare minimum required. The 8 elements are required to approximate this sine 4 pi x function with the linear polynomials. The next level will be this, certainly improved. We go for the next level, this is what we obtain. The solution is getting better. You see the improvement, you note the improvement, John?
Yeah.
Okay. Excuse me. Excuse me. Okay, we are reaching the limit here. Okay, it's ready now. Excuse me. Oops. One more over here. Okay, so we have run this program now, and you can see this is sufficiently smooth function now. This is the true representation of a sine 4 pi x function, sine 4 pi x on an interval 0 to 1. Okay, what we have used here, if you see, we have used 8,192 elements. The error in H1 norm is 0.00 approximately 4. And for L2 error, this is after 6 decimal places. What happens if I just take, for example, 4 refinements and I take my second order polynomial? This is my first case, second, third, fourth, and done. So basically, as you can see from here, the approximation here is almost as this one with 8,000 elements here. The error level is 0.0039, here it is 0.0031. Here it is slightly more, but okay, we can do one more refinement. The point what I want to raise here is that in both the cases, here we are talking about second degree polynomial. So each element will have 3 points with one overlap. So altogether we have 257 points. Here we had 8,193 points. The point here is that if you are having a smooth solution, smooth right hand side, then you can use always higher order polynomials and you get to the true accuracy or desired accuracy very quickly. So this was for the second order polynomial. Let's go for the fourth order polynomial and just talk about, say, like 2 refinements. Excuse me. This is my first level, second level, third level, and done. Okay, what we see here is that this value here in just in 3 iterations, 3 refinement levels, it has gone much smaller than as compared to this one. In fact, at the second level itself, it was much smaller than that. And here is basically much smaller than this norm also. And how many elements we are taking now? How many points? 32 times 4 plus 1, 129. Here it was 257. Of course, it is faster here also. We are finished in 7 seconds, 6.5 seconds. And here it was around 15 seconds. Here it was 39 seconds. Okay, so this reflects 2 points. One is that for a smooth solutions, you can go for higher order polynomials also, and of course your error will be much improved there. I will try to show you as comparison here. Just a moment. So it will now keep on changing, keep on doing it itself without any input from my side. I need to say something about the error, what we are obtaining, or the convergence of the solution to the true solution. It's done now. It was again the linear order polynomial starting with 8 elements and 10 refinements. Now with second order polynomial, here, and with the fourth order polynomial again here, just 2 refinements. So what I wanted to show here is that if you see at these numbers, with a linear polynomial here, the error here, it goes as the order of h. We halve our mesh size from 8 elements to 16, the error is almost half here. Again half here, mesh size, it's again half. So as we are increasing the number of elements or reducing the mesh size, this error in H1 norm is exactly going in that way. This is of order H. The L2 error is of order H square. You can see approximately this is a factor 4. So this is reduced from here by a factor 4 approximately. In the beginning it's a coarse mesh, then here 4, then here 4, then here 4, and it goes like that. In this case, it should be an order 4 here. It is a square. It is a second order polynomial, so it will behave like h to the power 2. So 2 times 4 is approximately 8 here. 5 times 4 is 2. 12.76 times 4 is around 50.96, you can see here. So this is converging to the solution with order h square, and this will be order h to the power 3, a factor of 8, you can see from here. If you go for fourth order polynomial, then it will be here simply order 4. From here to here, h to the power 4. It is when you are halving the mesh size, then it will go 16, a factor of 16. Here it will be a factor of 32. Okay, so this is what I want to show in this problem. Now my question to you is, if I change something here in this, do you see this line perfectly straight line, John?
Yeah.
Okay.
We can see
so
that.
My question is, yes, my question is that I chose 8 elements, linear polynomial, and no refinement, and I got here this H1 error and L2 error, they both are perfectly 0. What is the reason? Anyone has any idea? approximate the constant by a linear polynomial. This is just fine. If I make a change here, if I go to the linear polynomial and I again use the linear polynomial to approximate it, this will still be fine. Just in one element, even if I take the whole element as 1, I have a 0 error. So does this make it clear?
Yeah.
Okay, if I choose the second order polynomial and then I go with this one element linear polynomial, what I get here is there are error. It is not error free now. And if I start increasing, for example, 10 elements, then of course things are improving. Now it's the x squared function. And again, if I take here just one element but with a second order polynomial, I get perfectly 0 function here for the error. So this is basically general and for these 4 type of polynomials I have, 4 type of unknown functions, and you can basically in this function, this MATLAB function, I can define whatever specification I give. And you just need, okay, we always test our algorithms and methods basically on some known data, but of course you are not forced to use that. You can choose just the DDU here, which is the right hand side data, and the display data. And when you do not know the analytical solution, you cannot compute error, but you can trust that, okay, whatever data you will be giving, this program will be giving you the approximate solution of that problem without any basically other possible mistakes here. Okay, so that's the point I wanted to explain here about the numerical results. I will be uploading this one program. I will be able to use this TBE, Transborder Educators, to John and Neeraj, but I will need some time. I need to make it polished. For example, any student can understand what is happening here in this one. That may take 2-3 weeks of time. I will be away basically, but I will be sharing this program with all the students of this course.
Okay, that would be very useful. That would actually be very helpful.
Sure, my pleasure. So that's all from my side now. I'll come to the conclusion remarks now. I'm going to close this desktop sharing, John.
Yeah, that's all right, yeah.
We are back to the presentation here.
Yeah.
Okay. You might have felt that, okay, a little bit of feeling how you can use this finite element method to solve your problems. But this is just only the toy problem I have given to you. Very barely I have scratched the surface of the finite element method. There are very important things still remaining. What is that? We need to rigorously provide proofs for the existence and uniqueness of the solution of weak form and of finite dimensional formulation. A tool here is Lax-Milgram lemma. We need to provide the error estimation using the approximation theory from Sayre's lemma. A priori and a posteriori error estimates. A priori means when we can say something about from the given problem. A posteriori means what we can say about the error from the computed solution. And fast solvers, the matrix which I was able to solve here so quickly, it was from very small problem in 1D. When you are in 2D, 3D, higher order problems, things takes hell lot of time. So for that, for example, this conjugate gradient methods or multi-gradient methods one need to tackle. This is required for the linear system equations. And of course, more realistic examples in 2D and 3D. Of course, this I cannot include in this kind of model problem and model problem. It is, it takes a lot of time. And of course, this is difficult to share. The program, these are research level programs. But there are some programs, there are some finite element libraries available already. If you just Google through, you will find plenty of them written in C++. Some, I think, MATLAB programs may also be found.
You are now muted.
The mediocre teacher tells, the good teacher explains, the superior teacher demonstrates, and the great teacher inspires. John and Neeraj, let me know how the students are basically giving me a rating. I do not want them to be identified. Let them be anonymous. An anonymous rating will be deeply appreciated.
Yeah.
Thank you very much.
Yeah. Okay, thank you very much for the seminar talk. And so, any questions from any of the students or faculty that are gathered in the seminar room?
John, there is a question from the Legon in the chat window.
Okay. So, Tomar, there is a question in the chat window.
Chat window. Okay, hold on.
Yeah, it's asking what happens if we change. Yeah.
Just I have basically minimized the chat window here. I need to give some space to that. Oh, this is a video doc. I don't want that. Okay, what happens if you change the codomain to the complex space? You will have to solve the problem basically in both the spaces.
Okay.
So if you have some x plus iy domain, so then you solve the problem in x and y separately.
Okay.
It is fairly common in electromagnetic problems basically.
Okay. And also another question. You talked about you have a representative element and you have what you call isoparametric functions, right? From the representative element into
isoparametric mapping.
Yeah, but what about in the case where you are in 2 or 3 dimensions where you have a complicated domain? Can you explicitly write down what those isoparametric functions are, or you assume they are known and you work with that?
So basically, there are 2 questions here. One is that if you have select straight-sided domains, then you have a simple mapping.
Yeah.
But if you have a curved domain, so like the functions which we are using here, Lagrange basis functions or some higher order basis functions,
yeah,
to approximate you use those same basis functions to approximate your geometry, and this is why this name is isogeometric. So you can certainly approximate that. Provided there are some further constraints in that. I mean, the minimum angle, the interior angle, all those conditions are there.
Okay. So, any more questions from Legon? Margaret? Hello?
Yeah?
Yeah. Hello?
My apologies for taking a bit of long time. I wanted to share the numerical results also, so I'm sorry for a little delay.
No, that's fine. So let's ask Legon, do you want to put on the webcam and Dr. Tomar? Could you also put on the webcam so that they see who you are?
Yeah. No problem with that.
Yeah.
Okay, this is the webcam button here. Can you see me now?
Not yet.
Okay. You can see how a question.
A video is available from my side, John.
Oh, sorry, because the things that I don't have a camera actually on my computer, so that's fine. Sorry.
Okay. Anyone else confirm that they are able to see me? Neeraj, you?
No.